Alright, so we are going to continue with the chain rule. This is one of the most important rules in all of calculus, so that's why I'm spending a lot of time on this rule. Really, once you get accustomed to this rule, most derivatives become a lot easier. So previously we talked about different type of derivative rules with respect to x. So we had done examples like the derivative with respect to x of x cubed. We said that is equal to 3x squared. But with the full derivative, we also have to add this dx term on the end. Whenever we have something with x as the focus, the dx is just equal to 1 because the derivative of x is 1. However, if we have something like the derivative of sine of x instead of just x by itself, and sorry, I'll change that to a cubed, then this dx really comes into play. So what I do with problems like this is I really define what the inside of the function is. So in this case, instead of x, we have sine of x. So I define this as u. So I say u equals sine of x. And I rewrite the entire problem as the derivative with respect to u of u cubed. And I solve this integral this derivative because this derivative is a lot easier to solve. It follows into one of the rules, the exponential rule. And again, we can call this letter whatever we want. The actual rule is x cubed equals 3x squared, but it doesn't matter what this is exactly. So we can call it u. So the derivative of d over du, the derivative of u cubed is 3u squared, and we have to start writing this du, the derivative of the inside, which is u. And now we defined what u was. So we can really plug this in to find the answer pretty easily, and we get this is 3 times, and we said u was sine of x. And since we're squaring u, we square sine of x. But we still have to find du, or the derivative of u. So if we said u is sine of x, then du, or the derivative of u, is cosine of x. And just as a reminder, sine and cosine go through this cycle. So if you start with sine, you take the derivative, you get cosine. Take the derivative again, you get minus sine. Minus sine. Take the derivative again, you get minus cosine, and then you go back to sine. And so this is taking the derivative all down this way, and it goes through this cycle with 4 pieces in it. So following this cycle, taking the derivative of u, we get du equals cosine of x. And so now we have to add this last piece, du. So this is times cosine of x. And so our final answer is 3 sine squared of x cosine of x. Alright, let's do a couple more examples just so that we're in the practice of this. And so now let's take the derivative of cosine of x cubed minus 2x. So last time we had something raised to a power, some trigonometric function, which was sine raised to a power. As you can see here, now we are putting another function inside of a trigonometric function. But the process is exactly the same. We define what we want to be on the inside as u. So in this case, this polynomial x cubed minus 2x is inside of cosine of x, or is inside of the cosine. So we're going to write that on the side. We are defining u as x cubed minus 2x. Alright. And now we will rewrite the equation. So derivative of cosine of u. And this derivative is equal to minus sine of u du. Again, don't forget the du. You always have to multiply it. Multiply the derivative by whatever is the derivative of the inside to find the final answer. Normally, when you just take the derivative of cosine of x, you get sine of x, or minus sine of x dx, and the dx is 1, so that goes away, but this won't always go away. So we need to account for the du. So we already defined u as x cubed minus 2x. And we're going to find du by taking the derivative of u. And the derivative of a polynomial is pretty easy. You just follow the exponential rule for each piece. So for x cubed, we bring the 3 down to the front of x, so 3x, and then we subtract 1, 3x squared. In the second half of this, the minus 2x. The derivative of that is just minus 2 because it's just a constant times x, and the derivative of x is 1. So du is 3x squared minus 2. And we can plug both u and du back into the equation. And our final answer becomes minus sine of u, which we said was x cubed minus 2x. And all of that is multiplied by 3x squared minus 2. And that is our answer. Alright, let's try one more tricky one. This one might have a couple extra steps in it. And if you are following along, I think this would be a great time to pause the video and see if you have the, see if you are able to work through this problem. So the problem we're going to go through is the derivative with respect to x of sine of x times cosine of x. So really a trigonometric function inside of a trigonometric function. So if you do want to try a challenge, pause the video and see if you can get this one using the same type of u substitution for the chain rule. Alright, if you did give it a try, this is the solution to this problem. So like all of the other problems we did so far in this video, we are going to define the inside as u. So I'm going to rewrite this as the derivative of sine of u. And we're going to define u as x times cosine of x. And solving this derivative, the derivative of sine of u, we will get from the trigonometric rules, this is equal to cosine of u times du. Alright, so normally we would just plug in u and we would find du, but du is a little bit tricky because u has two parts. It has x and it has cosine of x. So to find du, we actually have to use the product rule again. And now if you remember, the product rule is the first part of the equation, x times the derivative of the second part, cosine of x. And so the derivative of cosine of x is minus sine of x. Minus sine of x. And then we have to add this to the derivative of the first part. So the derivative of the first part is dx, or just 1, times the second part, cosine of x. So I'm going to rewrite this down below. this is really equal to cosine of x from the second half, and then minus, and I'm just writing this in a different order because the minus is in the first part. So minus x sine of x. And that's our du. And I chose this problem because there are some derivatives you may have to take that have multiple steps. So this du might have to be in its own land, its own derivative problem. So this was a pretty simple extra derivative you have to find, but sometimes you could get into like a third or a fourth layer of derivatives you have to take just because the original equation is so complicated. But in this case we found u because that's what we defined it as, and we found du through integration. And now we just plug it into our original derivative and we get the final answer. So this is cosine of u. So cosine of, and we define u here as x times cosine of x. And then we have to multiply it by du. And du we found was this, cosine of x minus x sine of x. So cosine of x minus x sine of x. And that is our final answer. That is the derivative. That's the derivative of sine of x times cosine of x. So we started with kind of a short but complex equation, and we got a much longer derivative for the answer. And now the really nice thing about derivatives, and really calculus in general, is if you do have a good teacher, you shouldn't have to memorize too many of these rules. It's not really worth it if you move on to really real physics or real applied science. Nobody really cares if you have these memorized. Some of these simple ones you should have memorized, but there's no point to actually memorizing it. If you know how to use it, you know how to look it up, that's really all that matters. So hopefully you don't have one of those teachers that makes you memorize it just because they want you to. But this is the differentiation rule table I've been working off of just to teach this course a little bit. And we went through a lot of these general formulas in the first column. So we went through the constant, the derivative of any constant, so whether it's like 2 or pi or just any number, the derivative is going to be 0. We went through the sum rule, which basically means the derivative of two separate functions is the derivative of each piece of the function when it's added together. Same thing with the difference. If you have u minus v, and u would be some function of x, v would be some function of x, you get the derivatives subtracted from each other. In other words, you can distribute the derivative to each piece of it. Moving on to the constant multiple. So if you have another constant multiplied by a function, so for example, if we had 5x squared, the derivative would be, you could pull the 5 out of it, and then just take the derivative of x squared, for example. The product and the quotient rule are a little bit more complicated. If you have two functions multiplied together, like x squared and sine of x, you have to follow this rule. And same thing with x over sine of x, you have to follow the quotient rule, for example. The power rule is one of the easiest rules. You just bring the exponent down and then subtract 1 from the original exponent. The chain rule is the most important rule. That's what we've been going over. If you have the derivative of something, some function, which in this case is called g of x, inside of a larger function f of x, and this is really what we've gone over, so if we have like x squared inside of sine of x, then you take the derivative of the outside, multiply it by the derivative of the inside. We've been doing that for the past 2 videos. And then we've looked a little bit at the trigonometric functions, so sine and cosine of x, and that cycle. The rest of these, I personally don't have these memorized. Like I said, you don't really need to have them memorized, just as long as you can look them up when you need them. But these ones, I'm not going to go through every single rule there is. A lot of these you can just look at a table, and I would also recommend looking at a table that uses u instead of x, because not every derivative you take will have x as the inside. So in this case, you might be taking the derivative of tangent of x squared. And if that happens, you follow the u substitution, really like we've been doing this whole time. Or you might have, cotangent of sine of x or something. And the most derivative tables will have it in terms of u with du at the end, so that you don't forget to include the derivative of the inside. Exponential and logarithmic functions, these are a little bit more on the simple side. E to the x is really one of the nicest derivatives you can take, because the derivative of e to the x is itself e to the x. The derivative of natural log of x is 1 over x, and then these bottom two I really haven't used that much. But again, if you do come up with a problem that uses these rules, you can just consult the table, follow the chain rule if needed, and find the answer. And I'll give you an example of, we'll do this bottom left one, just to give you another example of following the chain rule with these. So let's say you have the derivative, so d over dx of, let's say, 5 raised to the power of x squared minus 2. So when I see this, I'm going to identify that we are taking the derivative of some constant 5, so some constant raised to a function with respect to x. And again, by function, I mean something that has an x in it, something that has some type of variable in it. So we are raising 5 to the power of some type of function. And what I would do, because I don't have these rules memorized for this specific case, I would look at a derivative table and identify that one rule here, the derivative of a to the x equals a to the x natural log of a, where a is a constant. And so I'm going to write that rule on the side. So d over dx of a to the x equals, and I already forgot it, it's a to the x natural log of a. So a to the x natural log of a, and really dx. Again, all of these rules do have a dx at the end, but a lot of derivative tables will just call it u instead of x. That way it's a little easier to use the chain rule if you're just beginning. Alright, so we said this original problem is in the same form as this derivative rule. And in this case over here, we have u is defined as x squared minus 2. So u equals x squared minus 2. And we can rewrite this derivative as d over dq of 5 to the u. And from the derivative rule up here, we know that this derivative is equal to 5 to the u natural log of 5 times du. And in this case, I'm just plugging in 5 for all the a's for the rule. So we get that this is the derivative. Now, since we did rename these as u, we do still have to plug back in u and du into the final answer. So we have a u here, and we have a du here. We already wrote down what u is defined as, because that's what we chose. And we'd still have to find du. So du in this case, since u is just a polynomial, x squared minus 2, du is pretty easy to find. So we bring down the 2 on the left-hand side, so 2x. And then the derivative of a constant here is 0, so plus 0. So du equals 2x. And now we have both x and both du, or sorry, we have both u and both du. And we can plug both of these back into our formula. So the answer that we end up getting is 5 times u, which we said was x squared minus 2, times natural log of 5, times du, which we found to be 2x. And that is our answer. So using u substitution, if we have a derivative rule that we find and we can match up with the derivative we're taking, it becomes a relatively simple process to use the chain rule and find the derivative. Again, I cannot stress enough, anytime you do take a derivative, make sure that you include this du or dx or d, whatever you are taking the derivative of. That is vitally important to getting the right answer for anything more than the derivatives that follow these rules exactly. On the right-hand side of this table, it does have inverse trigonometric functions, so inverse sine, inverse cosine. I'm not going to write an example for every single one of these. Again, like I just demonstrated, once you get the idea of the chain rule and know where to find these derivative rules, it's, as long as you know what to do, it's relatively simple to plug these in and solve most derivatives that a calculus class can throw at you. Same thing with hyperbolic functions, inverse hyperbolic functions, and parametric equations. And I think there I will stop the video for now, and we will move on through the topics in the next couple of videos. We're going to start applying these derivatives to separate, more involved and more applicable cases moving forward. So what we can actually do with calculus.